A profound thrum emanated from the quartet of mammary power plants, reverberating across the tarmac as Japan's inaugural heavy bomber, christened the Nakajima Shinzan, laboriously traversed a formidable 40,200 feet of reinforced concrete. Its unladen mass, a staggering 44,313 pounds, rendered it a full 8,000 pounds more substantial than its American counterpart, the B-17 Flying Fortress. Within the confines of the cockpit, the intrepid test pilot grappled with unresponsive flight controls as the colossal aircraft eventually wrestled its way airborne, ascending at a meager pace of barely 500 feet per minute, a rate half that achieved by contemporary American bombers. From the vantage point of the hangars below, Chief Engineer Kenichi Matsumura observed the arduous spectacle through his binoculars, his comprehensive notebook already replete with intricate computations that, in hindsight, ought to have foretold this challenging outcome. In 1939, the Japanese nation had procured the singular prototype of the Douglas DC-4E for a sum of $275,000, firmly persuaded that this acquisition represented the quintessential schematic for America's preeminence in aerial engineering. For a period of 2 years, an extensive process of reverse engineering had been undertaken, involving a multitude of highly skilled artisans and the finest raw materials Japan could possibly furnish, all dedicated to fabricating their indigenous rendition of American technological prowess. Yet as the Shinzan gradually receded into the ethereal morning mist, struggling perceptibly to sustain its meager altitude, a profoundly sobering realization crystallized. Merely replicating American advancements was, at times, wholly insufficient. A deeper comprehension of the underlying design philosophies and operational imperatives that guided America's engineering choices was fundamentally indispensable. Ask us to stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. The nascent rays of the morning sun stretched elongated silhouettes across the expanse of Oda Airfield as Kenichi Matsumura meticulously calibrated his stopwatch, poised to observe what the high command of the Imperial Japanese Navy confidently anticipated would serve as their definitive countermeasure to American strategic aerial bombardment capabilities. The calendar marked April 8, 1941, and the colossal Nakajima G5N Shinzan reposed majestically at the runway's terminus, resembling a veritable metallic peak. Its 4 mammary engines were already undergoing their preparatory warm-up, emitting profound, resonant growls that sent palpable vibrations coursing through the very concrete surface underfoot. For 18 arduous months, Matsumura had diligently supervised the meticulous installation of every single rivet and the intricate routing of every wire within this formidable aircraft. He was propelled by a singular overarching fixation that had pervaded and dominated Japan's entire aviation sector since the initial strategizing for the attack on Pearl Harbor had commenced. The United States possessed a crucial strategic asset that Japan acutely required: the inherent capacity to launch aerial assaults against industrial centers situated a formidable 2,000 miles from their operational airfields. The iconic B-17 Flying Fortress epitomized precisely what Japan found itself deficient in: engines that offered unwavering dependability, formidable defensive armaments, and, perhaps most pivotally, the expansive operational radius necessary to project military power deep into adversarial territory. Positioned adjacent to the runway, his clipboard clutched firmly, Matsumura observed Major Katsuaki Kira meticulously execute his pre-flight verification procedures within the Shinzan's command module. The immense bomber spanned an impressive 138 feet from its forwardmost point to its aft extremity, its lustrous silver aluminum fuselage shimmering brilliantly under the nascent illumination of dawn. Superficially, the aircraft's documented specifications appeared truly formidable: an estimated bomb payload capacity of 4,000 kilograms, an impressive operational reach of 3,500 miles, and an array of defensive armaments strategically situated to effectively neutralize any intercepting enemy aircraft. The naval acquisition specialists had heralded this aircraft as Japan's ultimate instrument of victory, an aerial platform destined to cripple American industrial capabilities. However, Matsumura's meticulously maintained engineering logs narrated a distinctly divergent account, laden with computations that had caused him considerable unease for several weeks. The aircraft's unladen weight registered at an alarming 44,313 pounds. Conversely, intelligence dossiers compiled from captured B-17G bombers indicated that their American counterparts weighed a mere 135 pounds in an analogous configuration, devoid of fuel or ordnance. This represented an approximate 8,000-pound increase in mass for the Shinzan to undertake essentially the identical mission profile, a substantial disparity that fundamentally contravened every tenet of aeronautical design he had assimilated throughout his 2-decade-long professional tenure. The formidable Momori engines crescendoed to their maximum output, emitting a deep, resonant sound akin to an unbroken peal of thunder. Each of the 4 radial power plants generated an impressive 1,070 horsepower, culminating in a combined output of 7,480 total horsepower, intended to elevate the aircraft's formidable 62,600 pounds at its maximal takeoff configuration. Matsumura, with the ingrained precision of an experienced engineer, instinctively performed the requisite calculations: a power-to-weight ratio of 120 horsepower for every 1,000 pounds of aircraft mass. In stark contrast, the B-17G, propelled by its robust Wright Cyclones, attained a superior ratio of 133 horsepower per 1,000 pounds. Furthermore, those American power plants had unequivocally demonstrated their exceptional dependability across hundreds of rigorous combat sorties flown over the European theater. With a decisive motion, Major Kira disengaged the braking system, initiating the Shinzan's ponderous takeoff sequence. The initial acceleration was notably sluggish, yet it gradually accrued momentum, a process that appeared interminably protracted. The colossal machine consumed 1,000 feet of runway, then 2,000 feet, and subsequently 3,000 feet. Matsumura's precise stopwatch recorded that the bomber devoured an exhaustive 4,200 feet of concrete surface before its nose wheel finally achieved liftoff. For comparison, a B-17 required only an approximate 2,200 feet under comparable operational parameters, less than half the runway distance, coupled with a fundamentally superior degree of inherent reliability. The Shinzan ascended with what could only be characterized as an exceedingly reluctant trajectory, accruing altitude at a paltry rate of scarcely 500 feet per minute. Simultaneously, Major Kira wrestled with flight controls that evinced a responsiveness akin to mechanisms immersed in a viscous, heavy oil. Through the magnified view of his binoculars, Matsumura distinctly perceived the pilot's headgear in perpetual motion, an indication of his ceaseless efforts to counteract the bomber's inherent inclination to lumber aimlessly through the atmospheric currents instead of maintaining a decisive, purposeful flight path. In stark contrast, American B-17s routinely ascended at a robust 900 feet per minute, with their flight crews frequently remarking upon the aircraft's palpable readiness and eagerness to attain its designated bombing altitude. As the Shinzan eventually receded from view, swallowed by the softening contours of the morning haze, its continued struggle to sustain its arduous climb, Matsumura at last grasped the profound scope of Japan's miscalculation. Merely 2 years prior, in 1939, Japanese diplomatic representatives had successfully acquired the singular Douglas DC-4E prototype for a substantial sum of $275,000, under the firm conviction that they had thereby secured the definitive schematic for American dominance in aeronautical engineering. This immense four-engine commercial airliner had initially appeared ideally suited for conversion to military applications, boasting an expansive 138-foot wingspan, robust all-metal construction, an advanced tricycle landing gear system, and a quartet of potent engines configured in a manner identical to that of the formidable B-17 bomber. Nevertheless, the DC-4E had previously faced unequivocal rejection from American Airlines, which had deemed it excessively intricate and prohibitively costly for viable commercial employment. Furthermore, major carriers such as United Airlines, Eastern Airlines, and American Airlines had each meticulously scrutinized the prototype and collectively determined that it was unduly robust, excessively engineered, and fundamentally inappropriate for lucrative passenger service. Thus, the very aircraft that Japan had mistakenly perceived as embodying the zenith of American technological prowess was, in reality, regarded as American industry's most significant and expensive developmental misstep. Matsumura's dedicated engineering cadre had undertaken the painstaking task of reverse engineering every singular component of the DC-4E with consummate exactitude, operating under the erroneous presumption that American design principles inherently prioritized sheer structural robustness above aerodynamic efficiency. Consequently, they had further strengthened structural elements that were already inherently over-engineered, incorporated additional defensive emplacements that augmented the aircraft's mass without conferring any tangible improvement in operational effectiveness, and integrated engines that, while generating sufficient power, were critically devoid of the inherent dependability requisite for protracted combat engagements. The Memori radial engines tragically succumbed to failure approximately every 50 flight hours, necessitating exhaustive overhauls that devoured precious, irreplaceable raw materials and highly specialized labor resources. In stark contrast, the Wright Cyclone engines utilized in American military service routinely performed for an impressive 400 hours between scheduled major maintenance interventions. Major maintenance was a persistent and debilitating concern. The irony surrounding Japan's ambitious aviation project was profoundly devastating. For 2 arduous years, and at the cost of millions of yen, the nation had dedicated itself to meticulously reverse engineering an aircraft design that American engineers had already deemed commercially unviable and subsequently abandoned. Japan's military adaptation efforts had only exacerbated the original design's flaws, rendering it even heavier and significantly more complex. Every intricate calculation meticulously recorded in Matsumura's engineering notebooks unequivocally corroborated the disheartening conclusions drawn from the morning's flight test. The Shinzan was fundamentally compromised, a magnificent testament to precision engineering misapplied to an inherently unsuitable foundational concept. A faint crackle of radio static emanated from the control tower, signaling Major Kira's routine positional report merely 20 minutes into his flight. While comprehensive service ceiling evaluations were scheduled for a later phase of testing, the preliminary data ominously suggested that the Shinzan would encounter considerable difficulty ascending beyond 24,000 feet under actual combat conditions. This was a critical disadvantage, as American B-17 bombers routinely navigated the skies at altitudes ranging between 25,000 and 30,000 feet, strategically leveraging this superior elevation as their primary defensive shield against intercepting fighter aircraft. The American heavy bombers effectively operated within an atmospheric band that contemporary Japanese fighters could barely attain, thereby transforming the very expanse of the sky into an impregnable defensive stronghold. As Kenichi Matsumura made his contemplative return walk towards the engineering hangar, his brilliant mind was already intensely engaged in dissecting the far-reaching implications of the morning's undeniable setback. Japan harbored an urgent and desperate need for strategic bombers, yet the endeavor to simply replicate American technological advancements had unequivocally proven to be an insufficient approach. The initial acquisition of the DC-4E had been predicated upon a deeply flawed assumption that merely possessing the enemy's hardware would automatically transfer the enemy's inherent operational capability. However, true capability, as Matsumura was rapidly realizing, resided not within the intricate lines of blueprints themselves, but rather within the profound industrial philosophy and manufacturing ethos that had originally conceived and brought those blueprints to fruition. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Please leave a comment about where you are from and what you think about the video topic. American aircraft designers were not merely engaged in the creation of functional flying machines. Their overarching objective was to engineer aerial platforms that could be mass-produced by the thousands, maintained with relative ease by minimally trained mechanics, and operated with unwavering reliability under the most arduous combat conditions by relatively young 20-year-old crew members. In stark contrast, Japanese engineers, driven by a different set of priorities, crafted what could only be described as masterpieces of intricate design. Aircraft that regrettably demanded constant, painstaking attention from highly skilled craftsmen. These Japanese creations, while undeniably sophisticated from a technical standpoint, were inherently fragile in their operational deployment. Consequently, the Shinzan, burdened by these fundamental design and manufacturing philosophies, was destined to never progress beyond the prototype stage into full-scale production. Even as Major Kira gracefully concluded his test flight and meticulously prepared for the final landing approach, Matsumura harbored a somber certainty. Japan's inaugural attempt to emulate American strategic bombing prowess had effectively failed before it had even truly begun to take flight. Yet, amidst the disappointment, a profound realization dawned upon him. This very failure, he mused, might ultimately impart invaluable lessons and strategic insights that the unblemished path of success could never possibly provide. With the arrival of spring, a renewed and palpable sense of urgency permeated Nakajima's Kisumi facility, driven by the Imperial Navy headquarters' unwavering and almost resolute conviction that Japan's nascent strategic bomber program could still, against all odds, deliver ultimate victory. Despite the Shinzan's undeniably disappointing performance during its trials, Admiral Isoroku Yamamoto's influential staff had issued a series of new directives that bordered on the realm of the impossible. The imperative to develop a formidable heavy bomber, demonstrably capable of reaching the American mainland, all within an ambitious time frame of just 18 months. Failure to meet this audacious deadline, it was understood, would signify the permanent closure of Japan's critical window of strategic opportunity. Kenichi Matsumura found himself immersed in an unrelenting schedule, routinely working arduous 16-hour days. His dedicated engineering team had undergone a significant expansion, now comprising over 200 highly specialized experts who had been meticulously hand-picked and strategically reassigned from every other major aircraft project across Japan. The Navy's profound faith in the Shinzan remained conspicuously unshaken, largely predicated on the impressive specifications meticulously detailed in official procurement documents. A substantial 4,000 kilon bomb capacity, an expansive operational range of 3,500 miles, and a formidable defensive armament consisting of 4 potent 20mm cannons complemented by 12 7.7mm machine guns. On paper, these formidable attributes suggested an aircraft fully capable of inflicting devastating damage upon crucial American industrial targets, stretching geographically from the remote Aleutian Islands all the way to the sun-drenched coast of California. However, Matsumura's accumulating flight test data began to narrate a distinctly different and increasingly troubling story with each successive mission flown. The Shinzan's maximum speed, a mere 261 mph, rendered it critically vulnerable to interception by virtually any modern fighter aircraft. Furthermore, its operational service ceiling, capped at 24,450 feet, left it precariously exposed to enemy interceptors that could launch attacks from a superior altitude with alarming impunity. American P-38 Lightnings, according to meticulously scrutinized captured intelligence reports, possessed the formidable capability to ascend to 39,000 feet and achieve blistering speeds exceeding 400 mph during their devastating diving attacks. Even more devastating than the aircraft's performance shortcomings were the pervasive engine reliability problems. The Memori radial engines necessitated complete and thorough overhauls after every mere 50 hours of flight operation, an intensive process that consumed precious aluminum alloy, a vital material that Japan could scarcely afford to allocate. Each of these complex engines contained components precision-machined to exceptionally exacting tolerances, demanding the unparalleled expertise of Japan's most skilled workers, master craftsmen, who were, at that critical juncture, desperately needed for the burgeoning production of Zero fighters as the conflict rapidly expanded across the vast expanse of the Pacific. To exacerbate matters, the Mamori power plants generated severe and persistent vibrations that relentlessly loosened sensitive instruments, caused critical fuel lines to crack with alarming frequency, and rapidly fatigued airframe structures at an unsettling rate. In stark contrast, the robust Wright cyclones, found in captured B-17s, exhibited wear patterns entirely consistent with a remarkable 400 hours of continuous operation between major maintenance interventions. The fundamental American engine design philosophy unequivocally prioritized unwavering reliability over raw, peak performance, willingly accepting a slightly reduced power output in exchange for dramatically improved operational availability and sustained readiness. This critical divergence meant that a B-17 squadron could effectively maintain full combat readiness for extended periods, often spanning several months at a time, whereas Shinzon bombers, plagued by their inherent design flaws and demanding maintenance requirements, would inevitably spend a disproportionately greater amount of time languishing in maintenance hangars than actively participating in vital combat missions. Matsumura's dedicated team had initiated meticulous forensic examinations of Wright R-1820 engines, carefully salvaged from B-17s that had been shot down over the Philippines. The profound differences in manufacturing philosophy between the two nations were immediately and glaringly apparent. American cylinders incorporated simpler cooling fin designs, ideally suited for high-volume automated production on sophisticated machinery. Conversely, Japanese engines showcased intricate and complex cooling patterns that necessitated painstaking individual hand finishing by highly skilled master craftsmen, a process that was inherently time-consuming and difficult to scale. American connecting rods were robustly forged from readily available, standardized steel alloys, while Japanese rods utilized exotic and specialized metallic compositions that, while potentially improving performance, inadvertently generated significant constraints and bottlenecks within the critical supply chain. The fundamental underlying problem, Matsumura realized, extended far beyond mere individual components. It permeated the entirety of the industrial approach. American aircraft manufacturers intrinsically designed for mass production from the initial drawing board stage, conceiving aircraft that could be efficiently assembled by a workforce requiring only rudimentary training, employing standardized tools and streamlined procedures. Japanese designers, however, optimized their creations for peak performance and artisanal excellence, resulting in aircraft whose construction demanded the continuous involvement of highly skilled artisans throughout every single stage of the production process. The inevitable outcome of these divergent philosophies was the creation of bombers that, while performing magnificently upon initial deployment, suffered swift and severe degradation when subjected to the unrelenting rigors of combat. These aircraft demanded incessant attention and specialized care from highly skilled personnel, whose replacement became progressively more challenging as the war intensified. By the summer of 1941, the ambitious Shinzon program had already consumed resources equivalent to the staggering cost of building 300 combat fighters. Yet this immense investment had yielded a mere 6 prototype bombers, production rates that had seemed entirely adequate during the tranquil peacetime planning stages, proved utterly and catastrophically insufficient as the global conflict escalated far beyond anyone's initial and most optimistic projections. The initial projections for Japan's heavy bomber program faced significant challenges. In stark contrast, American factories were already producing and dispatching B-17s at impressive rates of 20 aircraft per month from single production lines, with numerous additional facilities slated for activation as military orders escalated. The persistent weight problem that had afflicted the Shinzon from its maiden flight continued to exacerbate as further apparatus was installed. Armor protection for critical operational systems added a substantial 1,200 pounds to its mass, while improved defensive armament contributed an additional 800 pounds. Self-sealing fuel tanks, critical for enduring hostile encounters over enemy territory, further increased the empty weight by 1,500 pounds. Each modification intended to enhance combat capability invariably reduced the aircraft's already suboptimal operational capacity, creating a detrimental feedback loop where improvements designed for survival made the bomber too sluggish to evade the very dangers it was being protected against. Kenichi Matsumura's meticulous analyses revealed that a fully loaded Shinzan carrying its maximum complement of fuel and ordnance would grapple with sustaining elevation if even a single engine were to fail. Its twin-engine flight characteristics approached perilous conditions, and its single-engine performance rendered successful landing attempts highly dubious at best. Meanwhile, B-17 crews, according to comprehensive intelligence reports, consistently managed to return damaged bombers to base on two engines, sometimes even successfully completing their missions, and reaching their airfields after suffering the incapacitation of half their engines due to enemy action. The pervasive aluminum shortage, which began impacting all Japanese aircraft production with increasing severity in late 1941, struck the Shinzan program with pronounced intensity. Each bomber demanded a staggering 8 tons of aluminum alloy, in stark contrast to the 5 tons required for a Zero fighter, or the mere 3 tons for a typical Army bomber. Japan's total aluminum production capacity could hypothetically sustain the manufacturing of 12 Shinzan bombers per month, but only if no other aircraft were concurrently produced, a condition impossible under wartime exigencies. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. The practicalities of wartime imperatives meant that the voluminous manufacturing of heavy bombers was in direct contention with fighter programs that were critically essential for homeland defense. American aluminum production, according to intelligence estimates, surpassed 900,000 tons annually by 1943. Conversely, Japanese production reached its zenith at a mere 142,000 tons in 1944. Creating a profound material disparity that rendered large-scale bomber production unfeasible, irrespective of the inherent design efficiency. Even if Matsumura's dedicated team had conceived a perfect aircraft, Japan fundamentally lacked the industrial capacity to construct it in strategically significant quantities. The emotional toll on his engineering team became progressively evident as continuous test flights persisted in uncovering intrinsic deficiencies. Workers who had spent months refining distinct elements of the aircraft observed powerlessly, as their meticulous craftsmanship was nullified by inherent structural imperfections that resisted rectification via gradual enhancements. The Shinzan, it became clear, necessitated a total overhaul from foundational concepts, yet Navy acquisition timelines allowed no window for starting over from scratch. By autumn, Matsumura had arrived at an insight that he hesitated to articulate in official meetings. Japan, he realized, was constructing the inappropriate aircraft using unsuitable methodologies for an unsuitable strategic context. The Shinzan epitomized the strengths of Japanese engineering acumen, exact fabrication, meticulousness, and the refinement of discrete parts, but applied these strengths to an objective that required everything Japanese industry struggled with: mass production, streamlined upkeep, and designs engineered for consistent operation over absolute flawlessness. The captured B-17s, sitting in Japanese hangars, provided constant exemplars of an alternative methodology to aviation engineering. However, comprehending American design philosophy and putting it into practice represented fundamentally distinct obstacles. Japan possessed the technical knowledge to build superior bombers, but was deficient in the manufacturing framework to build enough of them to achieve strategic relevance. The captured B-17E reached Nakajima's facility via a procession of transport vehicles in March of 1942. Its aluminum skin exhibiting charring from the fighter attack that had compelled its descent in the Philippines. Kenichi Matsumura positioned himself near the hangar doors as workers skillfully guided the undamaged heavy aircraft inside, experiencing a confluence of eager expectation and occupational apprehension. For 18 months, his team had been deconstructing for replication the DC-4E prototype, presuming their grasp of American design philosophy. Now they would finally scrutinize the authentic article. The Flying Fortress appeared more compact than anticipated. Its wingspan of 103 feet presented a surprisingly slender profile compared to the Shinzan's colossal 138-foot expanse. Yet as Matsumura's inspection team commenced their methodical scrutiny, profound distinctions emerged in ways that disputed all preconceived notions about American engineering. The B-17's unladen mass of 36,135 pounds was a remarkable 8,000 pounds lighter than the Shinzan. Notwithstanding comparable provisions of defensive armament and fuel capacity, Matsumura directly oversaw the engine removal process, observing as technicians meticulously dismounted the Wright R-1820 Cyclone radials that had propelled this specific heavy bomber across thousands of miles of the Pacific Ocean. Each engine weighed 1,850 pounds and yielded 1,200 horsepower at takeoff settings. In contrast, the Shinzan's Memori engines weighed 2,100 pounds each and generated a more potent 1,870 horsepower, creating a power-to-weight ratio that appeared formidable until juxtaposed against American efficiency standards. The Wright Cyclones exhibited signs of usage that told a compelling testament to enduring functionality. Cylinder walls revealed uniform abrasion consistent with hundreds of flight hours, while connecting rod bearings showed negligible deterioration despite evident operational duress. Particularly astonishing was the uncomplicated nature of the cooling system design, straight fins fabricated using mechanized processes, rather than the intricate curvilinear configurations that Japanese engineers had presumed to be requisite for sufficient thermal dispersion. Disassembling the American engines uncovered a production ethos that stood in direct opposition to all principles Matsumura had been taught about exactitude in design and construction. Permissible variations were more relaxed than Japanese standards would sanction, yet these engines functioned with greater dependability than Mamori radials constructed to far more stringent parameters. American designers had apparently prioritized steady operational output rather than maximum operational capacity, embracing a marginal diminution in effectiveness in return for significantly enhanced ease of upkeep. The examination of the captured B-17 Flying Fortress revealed remarkable insights into its superior maintainability, a characteristic that quickly became a focal point of Matsumura's detailed analysis. The discrepancies in airframe construction, for instance, proved exceptionally illuminating. The B-17's wing spars, critical structural elements, were fabricated from aluminum extrusions, components that could be efficiently and economically mass-produced on industrial rolling mills. This design choice allowed for structural reinforcement to be strategically concentrated at points experiencing the highest stress, rather than being inefficiently distributed throughout the entire framework. In stark contrast, Japanese engineers had conceived the Shinzan's wings, utilizing intricate forgings each demanding individual machining processes. While these parts were theoretically superior in their inherent strength and precision, their production was practically impossible to scale for large quantity manufacturing, highlighting a fundamental difference in design philosophy. Matsumura dedicated extensive hours to scrutinizing the B-17's electrical systems, expressing profound admiration for the pervasive standardization that facilitated the replacement of any component with minimal specialized training. The wiring harnesses, for example, incorporated color-coded insulation and utilized standardized connectors, effectively eliminating any ambiguity or guesswork during critical field maintenance operations. Similarly, control cables were meticulously routed through easily accessible channels, featuring inspection plates at regular intervals, which empowered mechanics to swiftly identify and rectify issues. The Shinzon's electrical systems, conversely, necessitated highly specialized knowledge for servicing, employing bespoke connectors and concealed routing that rendered troubleshooting an arduous and time-consuming undertaking, significantly impacting operational readiness. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. Also, feel free to write a comment about where you are from and what you think about the video topic. The defensive armament installation further underscored another pivotal divergence in design methodology. The B-17's gun positions were engineered for swift installation and removal, featuring standardized mounts capable of accommodating various weapon types as mission requirements evolved. Its ammunition feeds relied on straightforward mechanical systems that seldom malfunctioned, even when subjected to the extreme stresses of violent aerial maneuvers. Japanese defensive installations, however, prioritized precision and formidable firepower through complex hydraulic systems, which, while offering enhanced accuracy, mandated unremitting calibration by highly skilled armorers. The flight control systems within the captured American bomber operated via a network of cables and pulleys, a setup that appeared remarkably rudimentary when juxtaposed with Japan's advanced hydraulic boost systems. Yet, American pilots consistently reported superb handling characteristics across all flight conditions. These mechanical controls afforded direct tactile feedback, enabling pilots to instinctively sense the approach of stall conditions, whereas hydraulic boost systems could dangerously obscure perilous aerodynamic attitudes until recovery became an impossibility. This very simplicity, Matsumura apprehended, was not indicative of lesser engineering prowess, but rather a testament to a more profound and effective design ethos. The philosophy behind the fuel system design articulated American priorities with unflinching transparency. The B-17's fuel tanks were constructed from uncomplicated aluminum sheets, fitted with rubber bladders that could be expediently replaced in operational environments using only basic tools. Its self-sealing capability derived from specialized rubber compounds that inherently sealed minor perforations, providing vital protection without relying on complex mechanisms that were prone to operational failure under the duress of combat. Japanese fuel systems, conversely, employed elaborate pumping and valving apparatus designed for precise fuel management. But this sophistication introduced numerous vulnerabilities, potentially immobilizing aircraft far from their home bases. As Matsumura and his dedicated team meticulously compiled their comprehensive analysis throughout the summer of 1942, he began to grasp the profound implications of Japan's strategic miscalculation. American engineers, he realized, were not merely crafting individual aircraft. They were conceptualizing comprehensive manufacturing frameworks capable of producing thousands of aircraft, utilizing a workforce with comparatively limited training. Every single component was meticulously optimized for high-volume manufacturing, ease of field servicing, and unwavering operational reliability, rather than chasing maximal operational metrics or refined aesthetic engineering. The numerical data presented an unsparing lucidity, painting a stark picture of the disparity. B-17 production had already achieved a monthly output of 48 units at Boeing's Seattle facility alone, with additional production lines slated for activation as military contracts rapidly expanded. Each flying fortress required approximately 15,000 personnel hours for fabrication, a figure dramatically contrasted by the 32,000 personnel hours needed to complete a single Shinzan prototype. This staggering difference meant that American workers could construct 3 flying fortresses in the same time frame Japanese craftsmen required to assemble just one heavy bomber. Comparisons in material usage were similarly stark. A B-17 consumed 2 metric tons of aluminum alloy, whereas the Shinzan demanded 1 metric tons to achieve a comparable operational capability. American designers had systematically eliminated superfluous material through a methodical examination of load-bearing dynamics, creating structures that were precisely engineered for requisite structural integrity without introducing excess weight that would compromise performance. Japanese engineers, on the other hand, had constructed frameworks that were arguably stronger than necessary, operating under the premise that superfluous robustness was invariably superior to an optimized design. The divergent maintenance paradigms became conspicuously apparent through a thorough examination of the captured bombers' logbooks, which had been retrieved undamaged from the wreckage. B-17 squadrons performed scheduled maintenance, using uniform protocols that could be completed by any qualified technician in an operational theater. Engine changes, for instance, typically took a mere 6 hours using common tools, while hydraulic system repairs necessitated only basic mechanical knowledge. Shinzan maintenance, however, demanded highly specialized personnel who understood the unique characteristics of each aircraft, rendering unit-level servicing unfeasible under challenging combat conditions. Perhaps the most telling insight concerned the American approach to battle damage repair. B-17 structures were specifically designed to degrade benignly, with structural compromise localized to predetermined areas that could be repaired with improvised field solutions. Aluminum skin panels could be replaced with sections cut from other aircraft, while structural repairs utilized standard aluminum angle stock, readily available from any industrial supplier. Japanese aircraft, conversely, required bespoke components fabricated to exacting tolerances, which made field repairs impossible and necessitated prolonged operational incapacitation of compromised airframes. By October of 1942, Matsumura had arrived at a pivotal realization poised to fundamentally alter Japan's entire approach to strategic bomber development. The B-17 was not a superior aircraft because of advanced technology or exotic materials. Its superiority stemmed from the fact that American engineers had addressed the pertinent challenge. Instead of striving to build the idealized aerial combat platform, they had crafted a bomber that could be mass-produced, readily serviceable, and capably piloted by average individuals amidst the crucible of conflict. The path forward was unambiguous, yet formidable. Japan needed to completely divest from the Shinzan Initiative and commence anew, fundamentally grounded in American engineering tenets. However, 18 months into the Pacific War, the temporal window for such radical methodological shifts was rapidly diminishing. The directive from the Imperial Navy headquarters reached Nakajima's Koizumi facility on September 14, 1943, outlining a set of requirements that seemed less like practical engineering demands and more like an audacious challenge. Kenichi Matsumura, a leading aeronautical engineer, meticulously reviewed the stipulations on his drafting table, quickly discerning that Admiral Yamamoto's command staff had in essence tasked his team with defying the very laws of physics within an impossibly tight 18-month time frame. The specifications were breathtaking: a maximum speed of 370 miles per hour, an unprecedented velocity for any existing heavy bomber globally, a service ceiling of 33,000 feet, an altitude sufficient to soar above the operational limits of most contemporary intercepting fighters, a formidable range of 4,600 miles with a reduced bomb load, enabling a round-trip journey to the American West Coast, and a substantial bomb capacity of 8,800 lb, enough to inflict catastrophic damage upon major industrial complexes. These directives appeared to be a fantastical compilation of desires, seemingly penned by individuals unburdened by the practicalities of power-to-weight ratios or the stringent constraints of aluminum allocation. Yet, Matsumura himself had dedicated a year and a half to the painstaking analysis of captured B-17s, and the critical insights gleaned from American engineering philosophy had coalesced into a profound and ground-breaking understanding. He realized that Japan's cardinal error had been in merely replicating American hardware, while conspicuously disregarding the underlying engineering methodology. The new bomber, officially designated G8N Renzen, or Mountain Range, would therefore completely abandon the established architectural framework of the DC-4E, and instead wholeheartedly adopt the foundational tenets of construction that had propelled American aircraft to such remarkable success. Working sessions that autumn frequently extended deep into the nocturnal hours as Matsumura's dedicated team systematically dismantled every preconceived notion and guiding premise that had shaped Japanese aircraft development since the 1930s. Conventional Japanese engineering had traditionally prioritized meticulous artisanal skill and the perfection of individual parts, often resulting in aircraft that were masterpieces of engineering ingenuity, but simultaneously logistical quagmires in terms of mass production. In stark contrast, American engineering emphasized cohesive, holistic design and streamlined manufacturing processes, yielding aircraft that were sufficiently robust and adaptable for large-scale fabrication, capable of being built by the thousands. We sincerely hope you are finding this historical account engaging. Please stay with us and watch the conclusion of this video. Your support in the form of a like and subscription would be deeply appreciated. We also invite you to share where you are from in the comments below, along with your thoughts on this fascinating topic. The G8N design that materialized from these rigorous developmental periods bore no resemblance to previous Japanese bombers. Aerodynamic simplicity, characterized by clean lines, superseded intricate aerodynamic contours. A single vertical stabilizer obviated the problematic dual rudder arrangement that had long afflicted the Shinzan's directional stability. Mid-mounted wings conferred inherent structural robustness, while simultaneously facilitating easier serviceability for ground personnel. Crucially, every single component was conceived with paramount emphasis on dependable operation. First, performance second, and manufacturing ease third, a complete inversion of established Japanese aeronautical design principles. The selection of the power plant was absolutely pivotal to the program's ultimate success. Rather than attempting to adapt existing engines, Matsumura successfully persuaded the Naval Acquisition Department to underwrite the creation of the Nakajima NK-9KL Homar radial, specifically tailored for the operational demands of the G8N. Each engine was projected to produce an impressive 2,000 horsepower at military power settings, collectively providing a formidable 8,000 total horsepower to propel an airframe designed to weigh 3,860 pounds empty. This power-to-weight ratio would finally achieve parity with American benchmarks, while simultaneously surpassing American operational capabilities. The Homar engines integrated critical insights gained from meticulous right cyclone teardowns, strategically prioritizing consistent functionality above maximum theoretical output. Cylinder cooling fins employed streamlined configurations that could be fabricated in large quantities, while internal components were manufactured to tolerances that harmonized meticulous accuracy with rapid manufacturing throughput. Supercharging systems were calibrated for superior functionality in the upper atmosphere, ensuring full power output at altitudes where intercepting fighters would contend with significant aerodynamic challenges to sustain coordinated flight. Airframe construction eschewed the intricate metal shaping processes and bespoke mechanical fabrication that had rendered the Shinzan economically unsustainable to manufacture. The primary structural elements of the G8N's wings were fashioned from aluminum sections formed by extrusion, capable of being produced using conventional industrial machinery, with structural augmentation focused at high stress points rather than dispersed uniformly across the entire framework. Skin panels were engineered for modular exchangeability using standard workshop implements, thereby enabling expeditious restoration of combat readiness in forward operational environments. The electrical system design embodied a profound comprehension, gained through arduous experience, of the exigencies of wartime upkeep. Standardized connectors and color-coded wiring obviated conjectural approaches during repairs, while readily reachable pathways allowed mechanics to diagnose malfunctions with alacrity. Power distribution utilized established, reliable power distribution architectures akin to those employed by American designers, rather than the intricate arrays of electrical relays and junctions that had made Shinzan electrical repairs an arduous undertaking, demanding expert intervention and protracted diagnostic efforts. Fuel system design accorded paramount importance to resilience in combat, without sacrificing the ease of servicing. Fuel reservoirs incorporated resilient, self-sealing rubber diaphragms that could be exchanged by unit-based technical personnel, while fuel pumps and valves were strategically located for convenient reach during scheduled maintenance. This sophisticated system provided meticulous regulation of fuel consumption for long-range missions, simultaneously dispensing with the convoluted automated mechanisms that had introduced numerous vulnerabilities to operational breakdown in earlier designs. Defensive armament placement meticulously harmonized offensive capability with the foundational strength of the airframe, thereby circumventing the burdensome mass increments that had afflicted earlier Japanese heavy aircraft designs. Gun positions utilized interchangeable attachment points conforming to uniform specifications that could facilitate the integration of various armaments, while the delivery of ordnance was managed by robust mechanical apparatuses that operated dependably, even during aggressive aerial maneuvers. This comprehensive installation provided all-encompassing defensive range without introducing aerodynamic resistance or excessive mass issues that would detract from the aircraft's aerodynamic efficiency. The first G-8N prototype emerged from Nakajima's final assembly hangar on August 23, 1944. Its silver aluminum skin radiating brightly beneath the incandescent glow of industrial illumination that had remained incessantly active for 3 months. Matsumura personally oversaw the rigorous pre-takeoff examination, meticulously checking systems that embodied a profound compendium of insights garnered over 4 years, concerning the essential elements contributing to aerial triumph in hostile environments. Test pilot Captain Teiichi Shirani executed its inaugural aerial maneuver on October 23, 1944, providing an assessment of its flight dynamics that surpassed every anticipation. A maximum speed of 368 mph at 26,245 ft affirmed the precision of the engineering projections that had foretold a parity with American operational standards achieved through Japanese industrial prowess. Service ceiling tests substantiated the airframe's capacity to function at 33,465 ft, significantly beyond the operational stratum where most intercepting fighters retained optimal fighting efficacy. Range testing demonstrated comparable excellence with a maximum distance of 4,639 miles substantiated through meticulously observed endurance sorties. The G-8N could indeed strike objectives situated along the western seaboard of the United States and safely revert to its operational hubs within the Mariana Archipelago, at last furnishing Japan with the long-sought capacity for strategic aerial bombardment that had been envisioned and pledged since the inception of the Pearl Harbor operational strategy. The initial stages of harbor planning were underway. However, even as the third prototype aircraft successfully underwent its rigorous acceptance trials at the Koizumi airfield in the nascent months of 1945, the overarching strategic landscape that had originally provided the impetus for the G-8N program was undergoing an irreversible and catastrophic deterioration. Formidable American B-29 superfortresses were relentlessly dismantling Japan's industrial infrastructure, systematically obliterating its capacity for production, while carrier-borne aircraft freely patrolled and operated across the Japanese home islands. The critical aluminum reserves, absolutely essential for the manufacture of the G-8N, were being peremptorily redirected to urgent defensive fighter initiatives. These programs offered a more immediate and tangible shield against the devastating bombing campaigns that were reducing major Japanese urban centers to desolated expanses of ash and debris. Ultimately, only 4 G-8N prototypes would ever be completed before Japan's unconditional surrender brought an abrupt and permanent cessation to the entire program. This advanced aircraft, which finally presented a viable solution to Japan's long-standing strategic bomber deficit, had emerged far too late to exert any meaningful influence on the conflict's ultimate resolution. A testament to engineering brilliance, rendered utterly obsolete by an unforgiving industrial calculus that no amount of technical ingenuity could possibly circumvent. Matsumura, a key figure in the project, observed with a heavy heart as the fourth prototype meticulously taxied to its designated parking position on August 10, 1945. He was acutely aware that American technical assessment teams would imminently arrive to scrutinize the remarkable achievements of Japanese engineering, particularly what it could accomplish when unshackled from the inherent constraints of merely replicating foreign designs. The G-8N, in its very essence, encapsulated the cumulative knowledge and sophisticated methodologies Japan had painstakingly acquired regarding the proper construction of aircraft. Yet this profound learning process, this arduous journey to master the right way of aviation manufacturing, had unfortunately consumed an inordinate amount of time, rendering its strategic significance ultimately negligible. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. Please write a comment about where you are from and what you think about the video topic. The momentous announcement of Japan's surrender reverberated throughout Nakajima's Koizumi facility precisely at noon on August 15, 1945. The news was transmitted via radio speakers that crackled with persistent static, as Emperor Hirohito's solemn voice conveyed to the Japanese populace that the devastating war had finally concluded. Kenichi Matsumura stood stoically within the engineering hangar, positioned directly beside the impressive 4th G8N prototype. He watched with a profound sense of resignation as his dedicated team of 200 specialized engineers and technicians grappled with the stark reality that 4 years of intense and unremitting development had culminated in Japan's unequivocal and unconditional defeat. Outside the confines of the hangar, the relentless American B-29 superfortresses continued their systematic and methodical destruction of Japan's remaining industrial capacity. Their distinctive contrails were starkly visible at altitudes that the G8N could theoretically attain, but would tragically never operationally challenge. The bitter irony was complete and inescapable. Japan had at long last successfully conceived and constructed a strategic bomber theoretically capable of matching American performance, precisely at the moment when American strategic bombers had finished dismantling Japan's ability to produce aircraft in any substantial or meaningful quantities. The stark numerical figures that irrefutably defined the program's ultimate and tragic failure were indelibly etched into Matsumura's memory with an almost painful mathematical precision. A mere 4 G8N prototypes had been successfully completed, a pitiful contrast to the staggering 12,731 B-17 flying fortresses churned out by American factories. These 4 aircraft represented the absolute zenith of Japanese engineering accomplishment, pitted against an American production line that, in a single month, delivered more bombers than Japan had managed to construct during 4 years of concentrated and arduous effort. American technical intelligence teams made their arrival at Koizumi on September 3, 1945. Under the leadership of Colonel Harold Watson, who hailed from the Army Air Force's Technical Intelligence Unit, Matsumura personally guided the examination of the G8N prototypes. He meticulously explained intricate design decisions and expounded upon the aircraft's performance characteristics to the American engineers, who approached the machines with a palpable professional curiosity rather than any overt sense of triumphant satisfaction. The captured German and Japanese aircraft they were diligently documenting represented profound technological achievements that had, tragically, manifested too late to sway the war's ultimate trajectory. Colonel Watson's comprehensive assessment, meticulously recorded in technical reports that would remain shrouded in classification for many decades, duly acknowledged the G8N's impressive inherent capabilities. Simultaneously, however, it underscored the severe industrial limitations that had inexorably sealed the program's fate. The aircraft's maximum speed of 368 mph demonstrably surpassed the early performance figures of the B-29 while its service ceiling of 33,165 feet admirably matched the stringent standards set by American heavy bombers. A projected range capability of 4,600 miles would theoretically have enabled striking targets within the continental United States from strategic bases located in the Marshall Islands. Nevertheless, these performance specifications, while remarkable, presented only a partial narrative. Watson's expert team painstakingly calculated that the manufacturing of a single G-8N demanded approximately 42,000 man-hours of highly skilled labor. This figure stood in stark contrast to the mere 18,000 man-hours required for a B-29 Superfortress, which was efficiently produced on Boeing's highly automated production lines. While Japanese craftsmanship undeniably yielded aircraft that were, in terms of individual components, technically superior, American mass production strategies generated aircraft that proved strategically decisive through their sheer, overwhelming numerical superiority. The subsequent material consumption analysis unveiled even more pronounced and stark contrasts. Each G-8N prototype, for instance, consumed a substantial 7 tons of aluminum alloy. In comparison, American heavy bombers, through systematic optimization of their structural design, averaged a more efficient 2 tons. Japan's total annual aluminum production in 1944 reached its peak at 142,000 tons, a quantity theoretically sufficient to construct 16,000 G-8N bombers, assuming no other aircraft were being manufactured concurrently. In stark contrast, American aluminum production in 1943 dramatically exceeded 920,000 tons, a colossal output that comfortably supported the simultaneous production of fighters, bombers, transport aircraft, and even civilian goods, all without encountering critical resource allocation conflicts. Matsumura frequently found himself in the position of elucidating to American interrogators the fundamental philosophical differences that had profoundly shaped Japanese aircraft development throughout the entirety of the war. Traditional Japanese engineering principles placed an almost obsessive emphasis on the absolute perfection of individual components. This approach invariably resulted in aircraft that were veritable marvels of precision manufacturing, yet simultaneously became logistical nightmares in terms of their production complexity. Conversely, American engineering prioritized the seamless integration of adequately performing components into highly effective and robust systems. This methodology facilitated the creation of aircraft that could be efficiently manufactured by workers possessing minimal specialized training, employing standardized and streamlined procedures. The comparative analysis of engine development proved particularly enlightening for the American technical teams diligently studying the critical lessons gleaned from the Pacific War. The NK-9KL Homar radial engines powering the G-8N each generated an impressive 2,000 horsepower, achieved through sophisticated supercharging systems that represented the cutting edge of Japanese technology. However, these engines necessitated complete overhauls every 120 flight hours, primarily due to inherent metallurgical limitations in their high-stress components. In contrast, the Wright R-3350 Cyclones, installed in the B-29, produced a slightly higher 2,200 horsepower, yet were capable of operating for a significantly longer 400 hours between major maintenance interventions. This remarkable operational longevity was a direct result of systematic reliability engineering, which deliberately prioritized consistent operational availability over the pursuit of absolute peak performance. The fundamental differences in manufacturing philosophies permeated every single facet of aircraft production. creating a stark contrast between two wartime adversaries. For instance, the formidable G-8N Renzan's wing spars were meticulously machined from solid aluminum billets, a process demanding highly specialized precision tooling that necessitated many hours of intricate setup time for each individual component. Conversely, the American B-29 Superfortress wing spars were ingeniously assembled from standardized aluminum extrusions and readily available sheet metal stampings, components that could be churned out in vast quantities using automated machinery, often operated by a workforce requiring only semi-skilled training. While the Japanese methods undoubtedly yielded structurally superior components, embodying a peak of individual craftsmanship, the American approach, prioritizing efficiency and volume, produced components that were entirely adequate for their purpose, and crucially, in quantities so overwhelming that they effectively nullified any marginal performance advantages the G-8N might have possessed. A comprehensive analysis of maintenance requirements brought to light the harsh operational realities of wartime, truths that had remained entirely invisible during the serene period of peacetime development and initial design. The G-8N's intricate systems, crafted with an emphasis on bespoke engineering, mandated specialized tools and highly trained mechanics for even routine upkeep, rendering squadron-level repairs utterly impossible under the chaotic and resource-scarce conditions of active combat. In stark contrast, the B-29's systems were deliberately engineered for ease of maintenance, allowing mechanics with only basic training to perform repairs using common, universally available tools found at any forward airfield. This critical design distinction meant that a damaged superfortress could often be swiftly returned to combat readiness within a mere matter of hours, whereas a similarly damaged G-8N would languish, requiring weeks of highly specialized repair work at major well-equipped maintenance facilities, effectively removing it from the war effort for extended periods. By October of 1945, American technical teams had concluded their exhaustive documentation of Japanese aircraft development programs, distilling their findings into profound conclusions that would indelibly shape post-war military procurement strategies for many decades to come. Their primary realization was a stark and uncompromising truth. Technical excellence, no matter how brilliant or refined, was strategically meaningless without the foundational bedrock of industrial capacity. Even the most sophisticated aircraft in the world, a marvel of engineering prowess, simply could not compensate for fundamental limitations in a nation's manufacturing capability and its judicious allocation of vital resources. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. Also, please take a moment to write a comment about where you are from and what you think about the video topic. The final interview between Matsumura and Colonel Watson unfolded on November 8, 1945, taking place in the imposing shadow of the fourth G-8N prototype, as American transport crews meticulously prepared to ship the aircraft to Wright Field for an exhaustive and detailed analysis. Their conversation transcended mere discussions of technical specifications, instead focusing intently on the overarching systemic factors that had ultimately determined the war's outcome. Despite the remarkable achievements Japan had made in individual aircraft performance, the brutal, devastating arithmetic of industrial warfare had, in essence, rendered even the most brilliant feats of engineering excellence utterly irrelevant in the grand scheme of global conflict. A particularly stark and sobering statistic underscored this reality. A staggering 4,250 B-17 flying fortresses had been shot down over Germany alone, a number that astonishingly surpassed the total quantity of all heavy bomber types combined that Japan had managed to construct throughout the entire duration of the war. This colossal disparity highlighted a critical operational advantage. American factories possessed the prodigious capability to replace combat losses at a pace far exceeding Japan's ability to even produce new aircraft, thereby creating a mathematical impossibility, an insurmountable deficit that no amount of individual technical sophistication or design brilliance could ever hope to overcome. Colonel Watson's conclusive assessment, meticulously recorded in a series of classified reports that would profoundly shape American understanding of industrial warfare throughout the nascent Cold War era, emphasized crucial lessons that extended far beyond the confines of aircraft development. His findings unequivocally demonstrated that ultimate victory belonged not to those nations capable of fabricating the very best individual weapons, but rather to those nations possessing the industrial might to produce perfectly adequate weapons in truly overwhelming quantities. The G8N Renzan, in its magnificent design and construction, represented the absolute zenith of what Japanese engineering could accomplish when theoretically freed from resource constraints. However, the harsh, inescapable reality was that resource constraints constituted the fundamental and defining characteristic of modern warfare. Matsumura watched with a profound sense of mixed emotions as the fourth prototype, the culmination of his team's tireless efforts, slowly disappeared into the cavernous cargo hold of an American transport aircraft. In that moment, he fully understood the ironic truth. His team's greatest technological achievement was destined to serve as a static museum exhibit, a historical curiosity for contemplation, rather than an operational weapon that could have altered the course of history. Indeed, 4 grueling years of intensive development had yielded an aircraft of immense potential, a machine that possessed the inherent capability to dramatically change the war's trajectory had it been manufactured in the colossal quantities that Japan's industrial base was simply never capable of achieving. The profound lesson, tragically learned too late, was devastatingly simple.